In this section, we'll discuss the capabilities of the iterated transform operator. It builds on topics introduced earlier in the intro series, so I recommend watching several sections before this one, including concepts, SDFs and combiners, repetition filters, and variables. We'll be using version 0.35 of the toolkit, so make sure you're using at least that version. Watch the first video in the intro series to see how to load the toolkit into your project. We'll start with a basic 2D SDF scene. We're going to use 2D SDF since it will be a bit easier to understand what's going on before we move on to 3D. We're going to run through these initial steps quickly since they aren't the focus of the video. Open the palette with the Alt-R shortcut and create a triangle SDF 2D. Change the shape to inverted isosceles triangle and set the height to around 0.8 and width to around 0.2. With this operator selected, open RayTK's Editor Tools menu with Alt-Shift-R. Choose Colorize 2D SDF. Then select the Colorize, open it again, choose Add Render 2D. Then select the renderer, open it again, choose Append Null. And then turn the viewer on the null so you can see the rendered image. On the render 2D, decrease the zoom a bit to around 0.3. Then on the colorize, set the inside period and outside period both to around 0.02. So that gives us a wider view and a better visualization of the distance values. So this was covered back in the 2D section of the intro series, but to recap, what we're seeing here is a visualization of the distance values produced by a 2D SDF. The red region is the inside, where the distances are negative, and green is the outside, where they're positive. And the lines in each section indicate the different levels of distance values. Before we discuss the iterated transform operator, let's first set up a similar approach without using it. Create an axis rotate and insert it after the triangle. Set the rotate amount to -20. Then create a reflect and insert it after the rotate. Now select both the rotate and the reflect and copy and paste those. And then connect the first reflect to the second rotate and the second reflect's output to the colorize. So first we're applying some rotation, and then we are reflecting it across the x-axis. And then we are doing that again, more rotation, more reflection. So if we wanted to do that 3 times, with this approach, we would need to make yet another copy of both of these operators. And if we wanted to synchronize the parameters so all the rotates are rotating by the same amount, we would need to use reference parameters or bindings or something. Iterated Transform provides a way to do this without having to make multiple copies of all the operators. Take the triangle SDF, the colorize, the renderer, and the top, and copy and paste those. And then connect up that triangle to the colorize. So let's create an equivalent to what we just did manually using iterated transform. So create an iterated transform operator and insert that after the triangle. Set the iterations to 2 and the reflect mode to just x. And then for the z part of the rotation, set that to -20. So that gives us exactly the same result that we got above. But if we want to repeat the process more times, all we have to do is increase this iterations parameter. So let's set it to around 5. This operator applies a series of transformations to coordinates before it calls its first input, in this case, the triangle SDF with the resulting position. It supports translation, rotation, and scaling, and can use a pivot if you want. But we're not going to be focusing as much on scaling in this video, more so on translate and rotate. This operator works in both 2D and 3D, which is why there is a z-translate setting here, which in this case isn't going to do anything, and there are rotation around the x and y axes, again, which in this case isn't going to do anything. In both this example and the original example, we're using reflection across the x-axis. So we could also change that to reflection across both the x and y axes. Or you could do x, y, z. It's going to be effectively the same thing in 2D. That also applies mirroring across the y-axis. That reflection is a key part of the iterated transform. To understand why, let's go back to our first example. Switch off both of the reflect operators using their enable parameter. And I'm just going to visualize this. Switching off the first one and the second one. So now what we have is effectively just a rotation by 40 degrees, since it's rotating by 20, and then it's just rotating by another 20. So without that reflection, you don't get any of that like duplication kind of accordion effect. So let's go back to the iterated transform. And if you, let's look at the output of that. And on the iterated transform, if you change the reflect mode here to none, you're going to end up with that same thing, where it's now just doing 20 degrees of rotation, in this case 5 times. So that reflect is important, and you'll see those reflection cut planes appearing in lots of different places within the resulting pattern. Let's try some more variations of the transform settings. To do that, I'm going to make a copy of this. So making a copy of all of those operators from the SDF through the top at the end, copy and paste those. And I'm doing that because we're going to be coming back to that original example later on. I'm adjusting the different parts of the translate parameter and see how that is spreading out the shape and also producing a more pronounced kind of accordion style effect where things get spread out and repeated. And also try different combinations of rotation there. So with different combinations of that, you can get a pretty wide range of effects out of this. It's worth noting that it's generally good to use smaller values because each one of these steps is taken for, in this case, 5 times. So if you're offsetting on the y by 2, it's going to be doing that 5 times. So larger offsets will tend to kind of expand things beyond the useful range, but depends on the use case. It's also worth noting that there may be cases where things disappear completely. And that's happening because the entire original shape ends up on the wrong side of one of those reflection boundaries. So every time that we apply reflection, we're effectively throwing out half of the space. So if all of the shape is in the half that gets thrown out, then nothing makes it through to the end. So it's important to keep an eye on the ranges that you're using in these things and make sure to keep them within ranges that don't cause everything to disappear unless that's an effect that you're going for. And especially if you're going to be applying animation to any of these, it's important to keep those within ranges that you know work. So when using this operator to create these kind of fractally shapes, I've found that you can get some good results by applying animated transformations before the iterated transform instead of during the iterated transform, particularly rotation. So let's create an axis rotate and insert that between the SDF and the iterated transform. And on the iterated transform, I'm just going to adjust the settings here to kind of spread it out a little bit more. Okay, so now if we go to that axis rotate and change that, you can see how you can get some continuous motion. So you could animate this with like a speed or something time-based, while the overall sort of structure and the places where it's being sliced and repeated stays the same. And when using this in a live performance context, I'll often set up MIDI controls for the different parts of the iterated transform, particularly the rotate, but those will be kept to a known specific good range. And then I'll use a pre-rotation like this with speed-based controls and then maybe a MIDI control for how fast that rotation is happening. That way you maintain more control over the overall layout of things while still having continuous motion. Now let's take a look at how you would use that operator in a 3D context. First, we'll set up a basic scene with ray marching. Open the palette and create a ray march render 3D. And then open the editor tools with Alt-Shift-R, tend null, to add a null top on the end so we can see the rendered image. Then select the renderer again, open the editor tools again with Alt-Shift-R, and under Add Camera, choose Look at Camera. And on the camera, let's pull it back to around 8 on the Z-axis and increase the FOV angle up to 60. Then create a box frame SDF and connect it to the first input on the renderer. And you may also want to go to the camera and move it, up a little bit and up to the side a little bit if you want to get a more three-dimensional looking view of the shape. Or you can just leave it in the center. So with that set up, we can get started with using the iterated transform in this context. So create an iterated transform, and then we're going to insert that between the box frame and the renderer. And so now when we try rotation there, we get a similar effect where certain areas get kind of sliced and repeated and extended, but it's happening in 3 dimensions. So we get 3 different axes that we can play with. So with different kinds of input shapes and different combinations of settings, you can get some really interesting effects out of this. You can also try using scaling. So if you switch on Enable Scale and then uh, adjust that uniform scale parameter, I find it to be a little bit hard to use in this context, particularly if you're scaling larger than 1, then things like expand beyond a usable size pretty quickly, and if it's too much smaller, they end up kind of disappearing. So I generally focus more on translate and rotation for this. We can also change the reflect mode here to something like XY to have it limit which axes we are applying the reflection to. So without any Z symmetry, you can get more variation of the front and back. Now try increasing the iteration count up to maybe 10. And I'm going to have to adjust the translate here to pull things back in. And again, that's happening because each of these transformations, the translate and the rotate, are being applied once per iteration. So if it's translating a certain amount, it's going to end up going that amount 10 times. In future versions of the toolkit, there might be an option to automatically divide those settings by the number of iterations, but that isn't currently available. Input SDFs, like the box frame SDF, produce interesting results since we can see through the hollow areas in the middle, and we end up just getting that outer frame showing up in different places. But you can also use other types of SDFs to produce more solid shapes. So let's create an octahedron and connect that instead of the box frame. So now going over on the octahedron, let's increase the radius a bit, maybe like 1.3 or something like that. So now, depending on the different settings we use there, we can create some pretty interesting forms there and really neat kind of fractal effects. And we can switch back the XYZ, so then we get symmetry along that axis too. Let's try adding a pre-rotation to this. So Alt-R and create an axis rotate. And then we're going to insert that between the SDF and the iterated transform. So now we can give it continuous motion. So you could use like a time-based expression here, like maybe 5 times Ebb's time flat seconds, or a larger number, maybe like 30. And that will give it this continuous motion while the overall shape is kind of remaining the same. So you can change the different layout of there, and it's always going to get that kind of continuous motion. Another useful input that I tend to use with the iterated transform in a 3D context is the polyhedron SDF. So let's create one of those. And we're going to insert that instead of the octahedron. And for now, I'm just going to switch off the axis rotate. So on the polyhedron, we have different settings for enabling different parts of it. So you could switch off faces, which is kind of the solid interior, and you can have it just use the sort of segment outlines. So that is sort of similar to box frame, where you have a hollow area in the center, this kind of shell that pops in and out of existence. Or you can have it switch on faces to give it that solid interior, maybe decrease the radius of that, and then use blending between the two. And that will give you some really interesting effects. And if we switch on the rotation again, there we go. And because we're not changing any of the settings on here, and this rotation is a periodic function over time, this is going to end up looping cleanly. So however often this rotation crosses 0 to 360, then it's going to be like an exact loop. Next, we'll discuss using field inputs on iterated transform to vary the translate and rotate for each iteration. To do that, let's go back to our 2D setup. So let's do the second one. Just copy all of that, paste it, and then look at the result. Field inputs on the iterated transform allow us to refine the transforms that are applied at each step. To make things a bit easier to interpret, let's go to the iterated transform and just zero out all of those if they aren't already. You can also use those parameters in combination with field inputs, in which case it will just add the resulting values, but just to make things a bit easier to understand, we're going to keep those at 0 for now. You can use any type of field that produces vector values for the translate and rotate inputs. So rotate one and then translate. For the scale, it takes in a float field if you're doing uniform scaling, or a vector if you are doing separate axes. We get a wave field, and let's set the axis to y. Now we need to convert this to a vector. So even though we're operating in 2D, it still expects to get a value for those other two axes. So let's select the wave field and open the editor tools with Alt-Shift-R, and then choose Rescale as Vector. And we can connect that up to the rotate field input. And note that the ordering of these inputs might change depending on which version of the toolkit that you're looking at, so just make sure to mouse over it and make sure that it's the right one. For the input low, change the first. For the input low, let's change all of those to -1. Since we're dealing with a sine wave, the values are going to be -1 to +1. And then for the output high, for the first two parts, we can set it 0. Doesn't actually matter what those are, but let's just keep it at 0 so things make more sense. And now we can adjust the high part of the range there. And you can also adjust the low end of it. So that will produce a variable amount of rotation at each step. Now let's try translation on the x-axis. Let's make a copy of the wave field and rescale, and connect that second rescale up to the translate input. And we're going to want to drop those values way down. And in this case, since we're doing translate, it doesn't actually use that z-axis. It's doing just the x and the y. So let's try changing the x. So you can have different amounts applied. You can also try changing the y, but things get a little bit weird there when you have a sine wave on the y-axis that's also translating along the y-axis, but it's worth experimenting with anyway. So what's going on here in the shader? So when the renderer is asking about a position in space, in this case, a pixel that it translates to coordinates, the iterated transform will first ask the rescale field how much rotation to apply. The rescale field will ask the wave will do its sine wave, rescale field will convert that to a vector and scale it, and then provide that value back to the iterated transform, which is then going to use the z part of that to apply rotation. Then it's going to ask the second rescale field for a vector. That does the same thing, comes back with another value, and it applies that as translate. Then it applies that reflection, and then finally it repeats that process again, and it does that 5 times. And then when it's done with that, it has that modified position, and it then passes that along to its first input, a triangle SDF, and asks it about that point in space. And it does its calculations, comes back with an SDF surface information, and passes that to the iterated transform, which gives it over to the renderer, and so on. It's important to note that although the iterated transform doesn't call that first input more than once, it does call the inputs to the field settings multiple times. So it'll be asking for a amount of rotation at every step. So all of the work that's in this chain upstream of whatever is connected there is going to be happening, in this case, 5 times. And we have another set of those are also being multiplied 5 times. So that means that if there is complicated work going on in those fields, then that's going to have a potentially significant performance impact. It's also worth noting that when the iterated transform asks for settings at each step, the position that it's asking about has the previous step's transformation applied to it. So when this wave field here is based on the y-axis, every time it's being applied rotation, its concept of where the y-axis is going to be changing on each step. So that can be used to produce some interesting effects. The fields that we used here so far are both based on part of the spatial coordinates that are being transformed. But the field can also be based on which iteration is being processed. To do that, we need to access the iteration as a variable from the iterated transform. So let's select the iterated transform, open the editor tools menu with Alt-Shift-R, and then under reference variable, choose normalized step. That'll create a new variable reference, and then for the field that we're using for the rotate input, let's get rid of that wave and then swap in that variable reference. Now, if you go over to settings there, it can be a little bit hard to visualize what exactly that's doing, but it's applying different amounts of rotation at each step, and it's doing that based on which step number it is. And because we're using the normalized index rather than just the index, it scales those down to a 0 to 1 range. So even though it's doing 5 steps, the values that come out of here are 0 to 1. And then we're scaling them up to whatever range that we've set here. Next, we'll discuss some more advanced options for symmetry and reflection. We're going to start by making a copy of the 3D scene that we had previously set up. So including the renderer, the camera, the SDFs, and all that. Move that down here, view the output, and then let's switch off the axis rotate for now and go back to the box frame. We can just get rid of these other two. And depending on what settings you have there, you may need to reset things so that things come back into view. So try some sort of different settings there so that you get some kind of changes without losing the shape completely. So just some combination of offset in the various axes and some amount of rotation. All right. To get a better view of this, let's use the inspector tool. So on the iterated transform, click this inspect parameter. And that's going to open up this inspector tool. And you can then use the mouse, the middle button drag to scale in and out, left button drag to rotate, basically the same as in a SOP viewer. So now we can see the different axes a little bit better. So when we're currently using that reflect mode in XYZ, it's showing the parameters of that selected operator in the panel here. So if we go to just X or just X, Y, we get symmetry along those axes, but not along the Z-axis. And then if we go with all of the axes, we get that additional symmetry. Let's close the inspector. So now if we wanted to use some other kind of reflection or symmetry, something like radial symmetry with a modulo polar. So that isn't one of the options that's available in this reflect mode setting, but Iterated Transform has a feature that lets us patch in our own custom transformations. In addition to the field inputs for the amounts of rotation, scaling, and translation, there's another input for a custom transform field. Let's quickly set one up, and then I'll walk through what it's doing. So we're going to change the reflect mode to none, and open the palette, create a position field, and then create a modulo polar, connect that to the position field, and then connect the output of that to the custom transform input. So depending on the settings that you have in there, you might end up with some render glitches in the places where it's applying that cutting. things get kind of messed up there. And if you recall back to the repetition filters video, we discussed how the mirroring is a way to fix those where shapes are getting cut off partway through. So on the modular polar, let's just switch on the mirror feature. Now we get our nice radial symmetry. So what's happening here when this is rendering? When the renderer asks the iterated transform about a point in space, the iterated transform first applies reflection, in this case none, then it applies translation, then it applies rotate, and the actual order of these is defined in the transform order parameter. And then once it's done those, it takes the current coordinates and it passes those along to the custom input. It says to the modulo polar, what coordinates should I be using instead? So modulo polar does its transformation on that position, and then it asks the position field for a value there. It just turns around, takes that position, spits it back to the modulo polar, which then returns it onto the iterated transform, which then replaces its coordinates with that new value. Then when it's done repeating that whole process some number of times, it calls into its first input and asks for an SDF surface result for that transformed point, and then forwards the result onto the renderer, which does the ray marching process. So when you're using the custom transform input, the coordinates are kind of flowing up the chain, and then this position field sort of acts like a mirror bouncing them back down the chain. So they come up as coordinates and then come back down as a vector field result. You can also use other types of transform filters in this custom chain. So here we're using it to apply this radial symmetry, but you could also apply other kinds of transforms. And if you want tighter control over the order of the different parts of the transformation, you could chain up, a translate and a rotate and whatever operators in whatever order you want here, instead of using the features built into the iterated transform. But regardless of what you do, it's generally worthwhile to have at least some form of symmetry involved, because otherwise it's just, applying transform multiple times and you don't get that like slicing and repetition effect. Next, let's look at the accumulation feature. So let's go back to our original 2D setup. Copy that. Make a copy of that, paste it, and then look at the result. On the iterated transform, let's change the reflect mode to just X. And then to make things a little bit easier to understand, let's change this triangle to be a hollow outline instead of a solid shape. So let's create an onion operator and then insert that between the two. And on the onion, bump up the thickness to around 0.05. And if you want, you can go to the render 2D and zoom in a little bit to get a closer view. Be like 0.5. As we discussed earlier on, the iteration aspect of the iterated transform refers just to how it transforms the point in a series of steps before passing that resulting position along to its first input. However, when the first input is an SDF, like in this case, there's a feature called Accumulation that calls its input on every step and combines the resulting SDFs. Let's go to the iterated transform and the Accumulate page, and then switch on Enable Accumulate. So now we're getting more of a copy of that shape at each step. And on the onion, maybe drop down the thickness to like 0.02. So in here, you end up with multiple overlapping shapes. And so what it's doing here is it's applying that transformation, then it's asking its first input for an SDF result, then it applies more transformation, it asks for another result, more translation, and so on. And then it uses this combine mode to combine the SDFs at each step. So you can also use something like smooth union and maybe bring down the blend radius. So you can use any of the different kinds of combine modes that you're going to see in other combine operators like combine or arrange. It's important to note, though, that we're now doing the work of everything upstream of that first input on every step. So that means here we have our iterations to 5. We're now doing this work 5 times as often. For a simple SDF like this, with just one kind of relatively simple transform on it, that is not particularly bad. But if you have a more complicated shape and more complicated types of transformation in there, it can add up to more of a problematic performance cost. So it's worth doing a comparison to see what the results are with and without accumulation. For example, in this case, if we are using this resulting 2D SDF as a cross-section for an extrusion with an infinite height, we wouldn't be seeing that inside area anyway, so all the extra detail that you get in the inside isn't really helpful. So if you just wanted to, provide a little bit of rounding on the outside, you could stick a round operator after it, and to get more of those slices effectively appearing in there, you could bump up the number of iterations. So it's worth looking at different options of whether to use accumulate in different scenarios to decide whether it's worth the performance cost. In all of the examples that we've covered so far, we've been applying iterated transforms to SDFs. But it can also be used on any type of field as well. So let's create a simple example with a 2D pattern. I'll create a weave pattern, then create an iterated transform, connect that up, then create a render 2D, and here, and then add a null top to the end. So here we're just using a 2D field that produces a pattern and just rendering that directly onto the output using render 2D. So to get a little bit wider view, let's drop the zoom down to maybe like 0.5. Now on the iterated transform, you can try out different combinations of settings, and you can get some pretty interesting effects. And if you increase the settings there, you can get some really neat kind of fractal effects there in 2D or in 3D. And you can also use this on basically any type of field that is based on position. And that could be in a 2D context or a 3D context. And it could be something like offsetting the surface of a plane or assigning color attributes or something. So you're not limited to just doing it in 2 dimensions, and you're not limited to just doing it with SDFs. That's it for this section. Stay tuned for the next video in the intro series. If you want to support RayTK development, check out my Patreon. You'll get early access to tutorials, exclusive scene downloads, and more. Thanks for watching, and as always, make sure to like and subscribe.